All right, welcome everyone to Ops 210, TwoSigma, Push Computing Research Boundaries with Google Cloud. I'm Alex, I'm a software engineer at TwoSigma.
Hi, I'm Dask. I'm a hedge fund customer engineer.
Hey, and my name is Maciej Kurzaski. I'm a product manager on Google Kubernetes Engine.
Great. All right, thank you so much for joining us. Again, I'm Alex Hayes. I'm an engineer on the team that builds and maintains TwoSigma's research compute platform. I'm fortunate to have the opportunity this afternoon to share my team's story. And it's the story of providing GPUs given just unprecedented demand. And it's a problem I'm sure many of you have experienced over the last few years. Then Dax and Maciej will introduce you to a new Google Cloud product, Dynamic Workload Scheduler, or DWS, that helps solve this problem. And then I'll cover how we integrated with DWS to acquire GPUs for our researchers. This is just a quick disclaimer saying this isn't financial advice. Let's get started. All right, so what does compute look like at TwoSigma? I think the best way to understand our compute platform is to get an idea for what it enables our researchers to do. And then this will be good context for you to understand our scale in GKE and how we run millions of jobs a day. Then I want to tell you about our challenges with GPUs in today's industry-wide capacity crunch. So TwoSigma is a quantitative hedge fund that develops and trades large data-rich strategies. These strategies are packaged up in something we call a model. And so here I'm highlighting the high-level pipeline for developing a model at TwoSigma. So where do we start? Well, TwoSigma researchers are scientists. So based on an observation, an idea, researchers form a hypothesis about how the markets might move. And then they'll explore this idea using techniques and data, and generally quite a bit of data. But they have to test and verify that their idea with this data makes sense. So they run these things, they run simulations. And these simulations are compute intensive. And with lots of researchers, it's incredibly compute intensive. And that's where a research platform plays its biggest role. And so after final review, successful models are then traded in the markets. Okay, so I've covered what we enable. Let's dive into what compute intensive really means. And so over the past few years, we've grown this platform to supercomputer scale. Our compute platform in GKE regularly exceeds 10 petabytes of concurrent memory and 1.5 million cores, and that's a lot of compute. And we do this with dozens of very large GKE clusters spanning multiple Google regions. And it offers users a wide range of machine shapes, including all types of GPUs in Google Cloud. And then we tune this environment for batch workloads. So these clusters aren't running web services. They're highly optimized to run a wide range of different batch compute workloads, including simulations. And so given the scale, the dozens of clusters and the diverse machine shapes, we have to make this easy to use for our users. And we do this with Cook. Cook is TwoSigma's own internal batch scheduler. And so Cook was created in 2015, so it's had a really long and important history at the firm. It originally started as a Mesos scheduler, but today it's evolved to orchestrate all of this compute in Kubernetes. So users submit workloads directly to Cook. Cook will queue them, rank them, and then launch them in our clusters. And Cook is capable of doing this millions of times a day, so millions of pods a day. It's capable of running a couple hundred pods a second or launching them, and it supports queuing hundreds of thousands of pending workloads. And so Cook is really the single integration point for researchers and developers at TwoSigma to run their workloads at scale. Cook's API saves every user from having to create and then manage their own infrastructure. It's centrally managed and it's run by an amazing team. And so it integrates with many open source distributed compute frameworks as well. So this includes Spark, Dask, and Ray. But it's also integrated with the rest of TwoSigma's platform, storage, and TwoSigma's own internal compute frameworks. And so that's a really quick overview of our platform. I want to switch focus to something that probably isn't news to a lot of you. So over the last year, the demand for GPUs has just increased dramatically. And we've all been challenged by this industry-wide capacity shortage. And this is true across many models, but it's especially acute with the latest ones, like NVIDIA's A100s and H100s. And so TwoSigma is no different from other companies that want to access and use these GPUs. And so platform teams are in a real bind, right? Where you're trying to satisfy user demand at a reasonable cost, or sometimes at all, and it's doing that in a highly constrained environment. So naturally, we face questions from users like, well, why can't I get GPUs? We use several different strategies to tackle a problem like this. One of them is just by shifting demand, right? So you can suggest to users, well, why don't you try another model like V100 or T4? They're relatively more obtainable. And this often works, but sometimes users just need more. They need more VRAM, they need their results faster. There are a number of reasons. And so some users can get away with the other models, but some users clearly need or benefit from these latest GPUs. And so helping these users in particular is really difficult because H100s and A100s are at this just entirely different level of demand and stock out. So I'm sure you've seen reports of companies stockpiling H100s. And you can solve this a number of ways. We consider a lot of them. And one of them is by buying GPU reservations in Google. But reservations are a long-term solution, and the GPU ecosystem is just rapidly changing. And then this reservation solution only gets worse when users tell you, well, I only need these GPUs for a limited period of time. In this situation, we would severely underutilize that reservation. And so you can see how platform teams are in a tough spot. So given unprecedented demand, this industry-wide capacity shortage, and understandable needs from users, what do? If you're facing these same issues, I think you're in the right place. We have some good news for you. So you're going to hear from our partners at Google about two really exciting new technologies that we use to solve this problem. TwoSigma is one of the first customers to use these new technologies, and I'll dive into that integration at the end of the session. But first, I'm going to pass it over to Dax, who will do a deep dive into Dynamic Workload Scheduler.
Thanks, Alex. Before we dive into Dynamic Workload Scheduler, I'd like to share something I hear from customers all the time as a customer engineer. It goes something like this. Dax, we have a great idea that we need 200 H100s to run for a few days, and we need them as soon as possible, and we can't start our job until we have them all. Can you help? And my answer before DWS was, well, it might be tricky. It might be tricky to get 200 machines or 200 cards immediately right now. We're probably going to have to grab them while we can, grab what's available, and then over time build up to the 200. And that can take time. That can take days or even weeks. And during that time, those machines are underutilized, and it's not a great way to optimize your cloud spend because you have them sitting around waiting for all the machines to come. With DWS, we make this problem a little bit better. I have a great answer to the customer. I could say you can use flex start mode, and everyone will be happy. So what is DWS, and why is the obtainability of scarce GPU resources like A100s and H100s so much better compared to on-demand? Well, there's a few reasons. For starters, DWS has access to additional capacity that is available via on-demand. When you ask us for a machine via DWS, you're going to let us know the region you want it in, the machine type and count of machines, and the runtime duration. That last one is really important. Knowing that we will get the machines released back to us at a certain time unlocks additional capacity as we can target DWS dedicated pools and expand across limited duration pools for unparalleled obtainability. To use DWS, you can leverage several integrations across GCP, and we continue to add to that list. First and foremost, you can use GCE directly via managed instance groups. You can leverage it with our Google Cloud Batch managed offering. You can use GKE, which we're going to hear a little bit more about in a bit, and Vertex AI training. There's two main modes to Dynamic Workload Scheduler. We have Flex Start mode and Calendar mode. To drill into Flex Start mode for a little bit, it basically offers just-in-time capacity for defined duration jobs. So in the example I mentioned earlier, when the request for all those machines just came to us and wasn't planned and we wanted them as soon as possible, Flex Start mode is the way to go. So basically, you're going to say, hey, Google, I need to run a workload for 2 days using 4 A100 machines with 8 GPUs each in this region. We'll put it in a queue, and as soon as we have them ready, we'll deliver them to you all at once, and you can run your workload. You don't have to worry about paying for idle resources while you build up to all those machines. In Flex Start mode, the max runtime duration is limited to 7 days, so if you need to run longer than that, you'll need to be able to checkpoint and save your data somewhere and start it up again with another request. It supports all GPUs in all regions, and you only pay for what you use. So in this example, if you requested these machines for 7 days, but you only used them for 2, and then you turn them off, you're only going to be billed for 2. Now on to Calendar mode. Calendar mode offers a simple way to buy a short-term reservation for optimized capacity. This option is great for users who need a guaranteed start time. So in this case, you're going to know the machines and region that you want to run in, but you're going to have a little bit of an advance notice. And you'll make the request to us, we'll approve it, and then you'll get them at that start time. Calendar mode is currently in private preview. It supports H100s. And you can get up to 128 GPUs, and you can get them for up to 14 days, which is a bit longer than Flex Start mode. In Calendar mode, you do pay for the entire duration of the reservation. So this is great for that use case where you know you have something you need to train maybe once a quarter at a schedule, and you don't need to purchase a reservation 24/7. You can just use this to save some money. With that, I'll hand it over to Maciek to talk about how GKE can integrate with DWS.
Thanks, Dax. So Dynamic Workload Scheduler is a foundational API or a capability that is built by our colleagues in the core infrastructure compute layers. And you still, when you run your workloads in a Kubernetes cluster or other service, you need other APIs that allow you to get access to it and orchestrate the entire interaction with queued provisioning of machines. So in Kubernetes, in Google Kubernetes Engine, we recommend 2 API surfaces that you should use to leverage the Dynamic Workload Scheduler. The one that probably will fit the needs of most of you is Kueue with a K. That's open source job scheduler built for Kubernetes that orchestrates the entire interaction with the Dynamic Workload Scheduler. Or, as an alternative to Kueue, you can also use an extension to the cluster autoscaler with a new provisioning request API, which is a more basic and foundational level API that, on one hand, will be most powerful and will give you the biggest level of customizability when it comes to interactions and building the entire workflow of leveraging queued VMs and queued provisioning. But at the same time, it also will require the most work out of you so that you can integrate it in your more maybe bespoke and customized solution that you might have in your company. So let's take a closer look on how to leverage these APIs and how the interactions will look like. Wrong button. OK, so first, maybe what is Kueue? So a couple of years ago, I think 2 or 3, we've recognized that Kubernetes really lacked a good job orchestration system that is cloud-friendly. And together with the open source community at Cloud Native Foundation, we've started the work on a project called Kueue with a K. That is essentially an add-on to Kubernetes that's performing the task of scheduling full jobs. So the core Kubernetes scheduler is capable of scheduling individual pods. And there are use cases where you need to make decisions whether something will be scheduled or not and will have access to the infrastructure on full workload level. The most common use cases are essentially various research platforms, batch processing platforms, where typically the end users, the researchers, they will create a very long backlog of jobs, way bigger than whatever the platform is capable of handling. And then you need a system which will, through policies and the defined configuration, decide, okay, these jobs can run, these need to wait, maybe these need to be preempted. This is how capacity gets divided between teams, and the full orchestration on workload level is performed. And that's the role of Kueue. If you want to learn more about it, it has a dedicated website, Kueue.sh. And here we're going to talk how do you really leverage it so that you can orchestrate the dynamic workload scheduler provisioning. Again, wrong button. First, what do you need to do to perform the configuration in here? The platform admin first needs to model the capacity in the cluster using cluster queues. So what you essentially do with the sample custom resource that configures Kueue that I'm showing here on the screen is that you need to say what's the amount of capacity and what types of machines and type of consumption model that your users will be allowed to use. And then Kueue looks at the backlog of jobs that want to get access to the cluster, wants to execute, and it verifies what resources they need versus the available quota, and then decides, okay, this job can be admitted, this one needs to wait, perhaps this one needs to be preempted because a more important workload is coming in the backlog, so we need to make space for that one. And on the workload level, so your researcher or end user on the end user system that is interacting with this needs to make two very simple levels of configuration. One, in a label, it needs to indicate that this workload should be orchestrated by Kueue using a certain cluster queue to provide the name in the first label that you see here on the screen as an example. Second important element of the workload that it needs to conform to is that you need to create it in suspended mode. Suspended mode is something like for the job API that we've added, I think 2 years ago also in anticipation for the need of capabilities like that, where you create the job resource, just the job definition in the cluster, but actually no pods get created by the job controller. There are no containers running in the cluster just yet. There is just only the information about the intent to run this job. And then Kueue with a K will be responsible for changing that flag. And the logic behind making that decision is going to be driven by available capacity, existing machines, and those various factors that you code into Kueue's configuration. So really, you just need these two elements in the workload. So on workload level, the integration with Kueue is very simple. And I'm showing the example of a job and how do you do it with a job, but you can also use various custom workloads or even bare pods. All they need to do is they need to have an API that allows you to get the semantic of suspension so that you create, you express the intent that you want to run this workload, but pods will get created only when Kueue allows them to be created. The whole tool and the whole system has quite advanced capabilities that allow you to build a very sophisticated and complicated batch processing platform where you can have multiple teams. These teams can have their own dedicated slices of the cluster. You may define policies where perhaps team A and team B have their own dedicated capacity, but they can also borrow from one another if the other team is not utilizing fully the capacity. You can model a variety of resource flavors like types of machines, shapes of those machines, maybe consumption models. Maybe you want to prioritize running on your reservation, but when you're out of that reservation, then you'd like low priority workloads to spill over to spot machines. All that logic can be coded into Kueue. But for the dynamic workload scheduler, what you can think about in here is that the core and the essence of what Kueue does is it takes a list of jobs that want to be executed and decides which need to be run when there is available capacity. So if you think about also the model that Dask explained with how dynamic workload scheduler works, where it simply looks at the incoming, in flex mode, it looks at the incoming requests to get VMs so that something can be executed on those VMs. And like, if these two layers, these two concepts can be connected for a simple API that could actually work jointly together so that Kueue recognizes what's the backlog of workloads that are coming in, and the dynamic workload scheduler can act on that and prepare capacity for those workloads. And the API to build that integration is a provision request. So provisioning request is an extension to the open source cluster autoscaler. So it's an API that will work on all clouds, but as you probably know, cluster autoscalers typically have custom implementations on every cloud. So GKE has its own cluster autoscaler that is well integrated and with lots of features that are baked into its logic of interactions with our infrastructure, while at the same time it still conforms to the open source APIs. And provisioning request is an extension to cluster autoscaler, which allows you through a custom resource to essentially express, hey, cluster autoscaler, I have this workload that I want to run with this spec. Can you make sure you're going to have resources for it? And actually, when you have them, can you send me a thumbs up so that I can trigger the workload? And there are a variety of use cases for it, but for the dynamic workload scheduler, we've built a special mode of operations for it. So currently, provisioning request has 3 modes, how you can enable it. The first and the simplest mode is you ask the provisioning request through a custom resource like the one that you see here on the screen. You ask it a question, hey, do you have capacity for this job? And it tells you yes or no. It's actually a very valuable mode of operations for on-premises use cases where capacity is fixed. You run your workload when you see that actually there's space for it. Then the second mode is meant more for cloud use cases where cluster autoscaler will check, does it have the capacity? And if it doesn't, it will resize the cluster so that you actually do have the capacity for it. And again, that's a very generic scale up of the cluster. And then last but not least, there is a special mode called queued provisioning where the cluster autoscaler will go to dynamic workload scheduler and tell it, hey, I have this workload coming in. Can you get plan VMs for me? And when you find them, let me know, and I will tell my users to start their workloads. And that's the mode that can be used, that is used by Kueue to get machines. You can also leverage provisioning requests yourself, so that you build the integration yourself and integrate it also in a more complicated or bespoke platform. Maybe as it may look complicated and with all of the code snippets that I've shown, let me show you on a simple example of a conversation how these all various components, how they interact together and how they provide capacity for you. So first, you have your user, right? This is a researcher, they want to run a workload. Maybe they use a notebook, maybe they use a shell script, create a YAML file, everybody loves them, with a job. And so they interact with the cluster and tell it, okay, please execute this workload for me. So Kueue recognizes that workload and accepts it if everything is okay, and sends information to cluster autoscaler through the provisioning request API. Hey, can you give me the necessary machines that are needed to run this workload? So cluster autoscaler picks it up and translates it into a request to the dynamic workload scheduler to dispatch it so that it can start looking for machines in our infrastructure that will be used to fulfill that request and run that workload. After a little bit of time, the machines get created. So dynamic workload scheduler gets the VMs and running. A cluster autoscaler recognizes that, so it attaches those machines to the cluster. Based on that, it is able to send the information to Kueue, telling it that the job can now be executed. So Kueue changes that suspended flag that you've seen earlier on the screen, that the workload can be triggered, and then job controller takes over, or whatever is the controller, like Ray job, and it starts to create pods and containers that will actually execute the necessary tasks. So after some time, whatever is necessary to actually fulfill the job, up to 7 days, as Dax mentioned, the workload gets completed. So on one hand, Kueue or whole Kubernetes system interacts with the user, confirming that the workload is completed. They get the necessary data that they wanted or whatever was the output of the processing workload. While cluster autoscaler kicks in and standard autoscaling mechanisms start to take over. So unless you want to run another job on these VMs, cluster autoscaler will just remove them, resizing the cluster down so that you don't pay unnecessary costs associated with using these expensive VMs. Now, this whole flow that I have shown you may look simple, but keep in mind that this is the happy path. This is what happens when everything goes well. And we all know happy paths are easy to implement. Things start to get funky when something goes sideways. Maybe the user cancels their request. Maybe something failed. How do I inform all of the components and cascade the information about the error everywhere so that then later it's debuggable and the system is in a healthy state still after the failure? All of that is covered for you in the implementation of Kueue, and it handles all of those interactions, greatly simplifying the entire effort and the experience necessary to integrate with Dynamic Workload Scheduler. As I mentioned in the examples, you've seen that this works with job controller, but we also support custom classes of jobs. We went on and worked together with various open source communities on implementing in the job set, in Flux, in Kubeflow, Ray. It also supports bare pods, which are typically used by workflow schedulers or orchestrators like Airflow. So you can use a variety of tools to orchestrate these jobs. And essentially, when you configure Kueue, you add those labels to indicate which cluster queue should be used. That's it. You don't need to do many changes in Airflow or in RayJob so that you can leverage AWS. It will just work for your users out of the box. And if you're interested in those more advanced features of Kueue, then a lot more is also coming. We very heavily innovate on the capability, adding there is a new release coming out every 2 months. Things like network topology over scheduling, multi-cluster queuing, more advanced algorithms for sharing resources in hierarchies, in cohorts to model more complicated enterprises and how they manage budgets, plus UX improvements. All of that is coming in here. Of course, if you don't need that, all you need is a wrapper that simplifies Dynamic Workload Scheduler. That is absolutely an option, and we give you all of the code templates and necessary to get started. The stuff that you will find on our website allows you to get going with your first initial POC within like 10 minutes of work effectively on this. And with that, I'll pass to Alex how they integrated with this.
Great, thanks guys for the great overview of DWS and Kueue. So these two technologies are really exciting, especially I think the open source collaboration. So I want to share with you now how TwoSigma integrated with DWS and Kueue to access A100s and H100s. So the integration primarily consists of two things. The first one is DWS node pools. And then the second is using Kueue to access the node pools and ultimately the GPUs through Cook. If you're not familiar with GKE, I'll just give you a quick primer on node pools. So each GKE cluster can have one or more node pools. And node pools are how you define a specific machine shape is available for your workloads to use. And so, for example, you can define a node pool with machines that have 64 cores, 500 gigs of memory, and 4 A100s attached. And so the first step to using DWS is to create node pools with DWS enabled. And you can do that pretty easily with just a single flag. So here in the CLI, enabled queue provisioning, or you can even do it through Terraform like we do. And that's really simple. This is really all you need to do on the GKE side. The second part to accessing GPUs is that you have provisioning requests enabled. So you have a couple options, as Maciek was just hinting at. One of those is by doing it the hard way, and that's using provisioning requests directly. So, like you said, provisioning requests are very powerful, but it's a very low-level API. Integrating directly with provisioning requests means you have to essentially build your own controller. You have to submit the provisioning request with pod specs that outline the shape of the nodes you want. Then you have to build a custom watch on those provisioning requests, continually check their status. If the request didn't fail, if it was actually provisioned and you actually have that node, then and only then do you submit, well, you can submit pods whenever, but you would then submit pods to consume those provisioning requests, and then they would schedule in the nodes. And then finally, you should do just some cleanup when you're done with the process. And so really, that's a lot of coordination. And it's not an unreasonable task for platform teams to do something like this. It just takes a bit of time and resources to implement. When we were doing this initial evaluation, we estimated that it would take us about 2 months to do it at our scale. But I want to show you an easier way, and that's by using Kueue. So using Kueue, accessing the GPUs through DWS is as simple as setting a label on your pods, right? So Kueue handles the complexities of creating and managing the provisioning request. And so here I've drawn a simplified diagram of how we integrated Kueue into Cook. So once you've installed Kueue and configured it to work with provisioning requests, the only active part of this is to submit the pods with that label, right? So to start the process, Cook will create pods, and it will set the label to the name of the cluster queue that you want the pods to go to. And they're configured to request GPUs. We've configured Kueue. Does this work? No. So we've configured Kueue to monitor the single cluster queue for pods. It's looking at the specs, and it's deciding, OK, so you're requesting this amount of GPUs. I need to create a provisioning request that actually will go out and scale that. And that's when the cluster autoscaler will pick up the provisioning request, and it will go to those DWS node pools we had created, and it will actually request nodes with those GPUs. Once the queue controller, which is watching these provisioning requests, sees that the nodes have been created in your cluster through DWS, it will then admit the workloads. So for jobs, it will unsuspend. For bare pods like us, it will remove a scheduling gate. And that's when the kube scheduler will actually see the pods, essentially for the first time, and it will schedule those on the provisioned GPU nodes. And that's it. Your workloads are running on GPUs. So this integration with DWS really had an amazing impact on GPU obtainability for TwoSigma. And I'm just showing a very short snapshot here, but we were experiencing some pretty severe stockouts for A100 GPUs. And when we integrated with DWS and Kueue in December, we improved obtainability for A100s on demand to 80%. And when H100s became available in January, we also enabled those through DWS and Kueue. And so I would confidently say that this integration with DWS and Kueue is what really unlocked these scarce GPUs for customers in our platform. And I think it does it at a pretty, it does it in an economical way, and it does it at really great scale. So yeah, thank you. That's it. We appreciate your feedback in the mobile app, and I think we have some time for questions.
We'd be happy to take your questions. And also, if you'd like to spend some time with folks from our product team or user UX researchers, we would really love to get your feedback. If you scan this code, it will ask you to fill in a short form that will allow you to schedule a session together with product or UX researchers working on GK.